Today we study ESA13H binomial theorem. The canonical delta, it is written as delta ij, that is the ij element of the n by n identity matrix, that is a matrix whose diagonal elements are all 1 and any other elements of diagonal elements are all 0. So that can be expressed as delta ij equals 1 if I and j are the same, and if I and j are different, then delta ij equals 0. Suppose we have two matrices. Multiplication of two matrices can be expressed as the product of ij element can be defined in this manner. So if I multiply a matrix whose rows are 3 and whose columns are 3, and this row, wait a second, each row of the matrix A has elements, for example, 3, then multiplication of A and B is defined only if the number of rows in a single column has the 3 elements. Because I have to multiply and multiply them and then add them all together. So number of columns in the first matrix and number of rows in the second matrix must be the same. Then the multiplication is defined. For convenience, right now we are considering the n by n matrices. So number of rows and number of columns are always the same. By the way, if I want to make use of the identity matrix, any multiplication of identity matrices will give a single result because it is a multiplicative identity. If I want to multiply two identity matrices, what I have to do is multiply two factors, the I something element, that means the k element. That k runs from 1, 2, 3, 4, 5, 2. So k runs from 1 to n. And I have to let these indices match together. And then j. This one shows that this is the ith row and jth column, and in the middle, kth column of the first and the kth row of the second factor must be matched, and k must run from 1 to n, and I have to add them all together. By the way, we know that identity matrix is the multiplicative identity. Any multiplication of identity matrix to any identity matrix will give trivial result that is the identity matrix itself. Therefore, its ij element of the product matrix is nothing but the canonical delta ij. So, therefore, we have proved this identity. In a similar manner, I can multiply the identity matrix to the right and to the left of arbitrary matrix. Therefore, if I compute A identity, that aik delta kj and sum over k from 1 to n. In a similar manner, I can always compute this like that, delta ik and akj. Okay, if I sum everything, every elements running from 1 to n for the k indices, then I have the same result, reproducing the matrix A, because the identity matrix, multiplicative identity matrix, has this property. Furthermore, what about the case if I multiply to, if I compute delta I, where I runs from 1 to n? That means delta 1, 1, delta 2, 2, and so on, until the end, that is delta nn. We know the two indices are the same, then everything is 1. I know that diagonal elements, there are n diagonal elements in the n by n identity matrix. The result is n. We call the sum of diagonal elements of a square matrix. Square matrix means the number of rows and number of columns are the same. In that case, the sum of the diagonal elements that can be written as a sigma. This is the trace, and the symbol of the trace is Roman capital letter T and small r, that means trace. Next, we compute the derivative of x to the n. We take the total differential of both sides. The total differential, Leibniz rule. What is the Leibniz rule? Total differential of a times b is a times total differential of b, and b times the total differential of a. This is something like the area of a rectangle whose two sides are a and b. Why don't we vary a single side with a small deviation and the other side with small deviation? That is the differential. By the way, the area, this is the original area, and after shifting the side from a to a plus dA and b to b plus the dB, the change is a plus dA, b plus dB subtracted by ab. That is the differential change in the area. You know what's that? This is a BDA, and this is ADB. Trivial. And this crossed one. This one is the DA and DB multiplied. If we assume that A and B are finite and DA and DB are infinitesimally small, then this term, this contribution is vanishingly small in comparison with either this or that. As a result, in the infinitesimal limit, this differential is ADB plus the BDA plus DADB, but it is this DA is of order epsilon, very tiny. So this is order epsilon, this is order epsilon, but this is order epsilon times order epsilon, that is order epsilon square. In the limit, as epsilon goes to 0, this one does not contribute at all. In the limit, dA and dB are both going to 0. That's the reason why we have the Leibniz rule of the product of the derivative of the product is like this. In case A equals B, the expression becomes quite compact, so A squared. And these two are the same. I have a factor of 2, ADA. We can extend this to compute the total differential of A cube. That can be done by substituting A equals A and B equals A squared. So dA squared, A times dA squared and A squared times dA. We know dA squared is a 2ADA, and this is A squared dA. Sum them all, we find 3A squared dA. We can make use of mathematical induction. Then we can finally prove this trivial result, that is the total differential of A to the n is n times A n minus 1 dA. And this is a way to prove this formula using mathematical induction. At the end of the day, we can repeat this calculation by assuming this n for a single n result for an arbitrary case. Then the next step will find the same rule is achieved for the next n. This one is identical to the result when we substitute n plus 1 for each n. Hence the assumption is true, and we have shown that A to the nth order, that A to the n, its total differential is like that for any A. So this is the case when we have a power of n of a variable x, then the total differential of x to the n is identical to this of whatever positive, non-negative integer. In the special case, A to the 0, we have a constant. A constant does not have any differential, is identical to 0. So when n equals 0, this factor becomes 0. So this formula is valid for any non-negative integer. We find the derivative. We have replaced this integer with a rational number. For simplicity, we consider m and n are both the positive numbers, positive integers. Okay, in that case, y to the n is identical to x to the m. We can make use of the result we just have found. Because m and n are both integers, we can compute the total differential of both sides. Trivial. And then we take the ratio. So differential of y and differential of x are correlated with over a factor. Now we can return to the original definition that y equals x to the m over n. So substituting this result for y, and I can compute dy over dx, and replacing this after substituting this expression for y. Final result is identical to the result with the integer n. What we have done is replacing n by n over m. Okay. This result is identical to this case, except that we have replaced this power with a rational number. Finally, we have shown that this derivative rule is true for any integer, especially for positive and 0. And actually negative case, except for the point x equals 0, everywhere is well defined. And then we have found that in case the power is a rational number, still the formula is true. But we remember we have computed the square root of 2 with an arbitrarily small accuracy, a small error. We can reproduce this square root of 2 that is irrational number. So we can find an approximation, a very accurate approximation of any real number, including irrational number, in terms of a rational number. Therefore, we expect x to the alpha, where alpha is a real number, its derivative should be of the form, this is our guess. This is our guess, and it will be found to be true in the next step. That's it for today. Thank you.